alaikum dear students. Welcome to Thin Film Technology course, lecture number 9. And this lectures, again, we will proceed with the vacuum technology. But here in this particular section, so we will discuss about the vacuum measuring devices that we call vacuum gauges. I mean, in this section, we will discuss about different types of vacuum gauges, their working principles, and their vacuum ranges and application, and which these kind of gauges can be utilized. Before to go into full details of the vacuum, before to go into full details of the particular kinds of the vacuum gauge, let's have a graphical view that specifying the range and utilizations of each kind of gauge. I mean, here you can see that we have specified different a vacuum range from 10 raised to power minus 3 to 10 raised to power minus 9. And here we have given different kind of the gauges. That is, we have a mercury manometer gauge, and this gauge here you can see that it can be utilized in a vacuum range that is from 10 raised to power minus 3 to 10 raised to power minus 2. Then we have a diaphragm, and the diaphragm it can be utilized almost from 10 raised to power minus 3 to 1 atmospheric pressure. And then we have, I mean, here you can see by yourself, we have the Pirani gauge, and here you can see that it can be utilized almost, the vacuum range of 10 raised to power minus 1 to 10 raised to power minus 5. Then we have the pinning gauge, and you can see here the range of the pinning gauge in this. Here you can clearly observe the range of the pinning gauge, and then you have the iron gauge, and the iron gauge is basically, it has a range from 10 raised to power almost 10 raised to power minus 2 to 10 raised to power minus 9 and beyond. So this is how, we have different kind of the gauges, and how they operate in different vacuum ranges. So vacuum systems, what are the vacuum gauges for? What for the vacuum gauges can be utilized? So be remember, a vacuum system must be monitored constantly to ensure satisfactory performance, but manufacturers seem to be reluctant to provide gauges which allow this to be done. So what actually we should do? Uh, Many different types of the gauges are available because each only covers a limited range of the pressure, and that this fact we have already specified here. That what kind of gauge is operated, is operated in what particular range. That's why we have different kind of the gauges. Never trust a gauge unless you can check it independently. Whenever you're trying to buy a particular kind of gauge, so never trust on the buyer or the supplier until you independently check, the working and the range of that particular kind of the gauge. So this is the special precautions we normally give to our students whenever they're trying to buy the apparatus or they're trying to deal with the supplier. So vacuum gauges can functions by one of the following mechanism. We have the mechanism for the vacuum gauges, and at least one of these mechanism can be followed by a particular kinds of the vacuum gauge. So the first is, uh, the first principle are the functions, which can be followed by a particular kind of gauge, that pressure exerted on its surface with respect to a reference. This is the functions. The example of uh, this kind of gauge is capacitance manometer gauge. Capacitance manometer gauge is basically, its function is like pressure exerted on the surface with respect to a reference. This is the something you can call the working principle of the capacitance manometer gauge that we will discuss later on in this lectures. Then thermal conductivity of a system gases, for example, thermocouple and Pirani gauges. In this particular gauges, we measure the thermal conductivity of the system gases. And Number third, we have ionization and collecting of ions. For example, hot and cool cathode ionization gauges. I mean, these are the three basic type and functions. Which basically result for a particular kind of the gauge. So, whenever you're trying to choose a particular type of gauge, so you must remember, or you should consider the following. You should consider the following fact. That is, you should know, the interaction with the chamber environments. You should know the interactions of that particular chamber, that particular gauge with the chamber environment. That is, you should know about the magnetic field, how much the magnetic field that particular gauge has, working temperature of that particular gauge, mechanical vibrations, and corrosive gases. These are some of the interactions with the chamber environment, and these kind of things you should look for whenever you're trying to choose a gauge. And particularly, you should also look for the pumping speed and how it will affect the measurement of the pressure. So let's first come toward the first type of the gauge that we will discuss here in this particular lecture. That is called capacitance diaphragm gauge. So here you can see, the external structures that how from the external the diaphragm gauge look like. So it has this kind of particular structure. It's a picture of a standard capacitance diaphragm gauge, and this is how it looks from internal. Internally, we have specified each of its part. That is, this is the connection part. With the help of which we can connect it to the uh, uh, something like with the help of which we're trying to connect some other system or some other parts. And here, this green-like structure is basically the measurement electronics. This particular section, this is the gather, and here, I mean, the red-like shape. You can also observe is something like a gluing structures. This rectangular shape here below and above. This is basically the heater which provides the heat. And here, this bow-like structure is basically a sensor diaphragm. This is the key. Just because of that, the gauge name is capacitance diaphragm gauge. And here, this portion is basically the refractive reference vacuum, and this is the electrode. You can see it here. This is the electrode, and this particular sections, I mean, uh, uh, this one is the baffle, and this section is basically goes to vacuum system. This goes to the vacuum system, where you want to create the vacuum. So let's start our formal discussions. About the capacitive diaphragm gauge. What is the capacitive diaphragm gauge and how we can utilize it? So it's basically a form of gauge which it allow an absolute direct measurement of the pressure. That is, the reading is independent of the gauge species. It operates in the range of 10 raised to power minus 5 to 10 raised to power 4 millibar. Electrodes are placed in a vacuum of approximately 10 raised to power minus 7 millibar. It's here it's saying that the electrode, these are the electrodes, and we remember that these electrodes, they can be placed in a vacuum that is approximately equal to 10 raised to power minus 7 millibar, and it should be maintained by the gather. This vacuum here we say that this thin layer is basically uh, here. This thin layer is basically the gather, and we say that this vacuum is being maintained by the gather. The capacitance, uh, the capacitance varies under the deflections of 25 micron thick diaphragm. You can see it here. This whole structure. It's the diaphragm. It's the diaphragm, and the capacitance varies under the deflection of 25 micron thick diaphragm due to the vacuum force. The vacuum force basically compel this diaphragm. I mean, compel it for the deflection. So as a result of that, the capacitance varies. That is, the pressure and the vacuum system basically responsible for the deflection of this 25 micron thick diaphragm. So the sensitivity of diaphragm deflection is 0.4 nanometer. That is, these measurements correspond to 10 raised to power minus 4 picofarad. This is the sensitivity of the diaphragm deflection, and it is the capacitance, the corresponding capacitance of this kind of the gauge. So its sensitivity to thermal fluctuations, uh, a thermostated housing is used, and it's approximately equal to 45 degrees centigrade. Let me repeat it again. It is sensitive to thermal fluctuations. This kind of the gauge, so it is sensitive to thermal fluctuations. That is, thermostated housing is used at almost a temperature equal to 45 degrees centigrade. A temperature around about 45 degrees centigrade. So uncertainty, it also have uncertainty, which is equal to 0.32, almost 10%, with accuracy equal to 0.15%. This is all about the capacitance diaphragm gauge. Then we have the Pirani gauge, and you can look at here at the diagram of the Pirani gauge, at how it looks like. And how we describe the functions or different parts of the Pirani gauge. So the main part of the Pirani gauge are, the first part we have, it's called, the first part in the Pirani gauge, is common. Uh, it's a chamber which includes a platinum filament. You can see it here. We start the discussion of this kind of gauge from this particular section. That is a Pirani gauge chamber which encloses a platinum filament. And then we have a compensating cells, which is here. This is the compensating cell. So what is the function of this compensating cell? A compensating cell to minimize variations caused due to ambient temperature changes. This is the functions of the compensating cells. So the function of the compensating cell is to minimize variation caused due to ambient temperature changes. Then we have the Pirani gauge chamber. The Pirani gauge chamber. This is the Pirani gauge chamber. Here this whole housing. Here, this is called the Pirani gauge chamber. We remember this thin wire. Which almost look like a resistor. This is the filament, and it's been made from platinum. But this whole case, this whole rectangular box, this is called a Pirani gauge chamber, and the compensating cell. This is the compensating cell. The compensating cell is housed on a wheat-stone brass circuit, as shown in the figure. This Pirani gauge chamber and compensating cell, they are being housed and on a wheat-stone bed. The circuit look like a wheat-stone bed. Here you can see it. You have studied the electronic course, so you can easily understand the structures. These two housing, that is the gauge chamber and the compensating cell, they are being housed in a wheat-stone bed. So how we understand the performance or the operations of the Pirani gauge? You already understood, you already know about the different parts of the Pirani gauge. So now, how the Pirani gauge operates? I mean, we discussed the operation of the Pirani gauge. So what we have, a constant current pass through the filament and the Pirani gauge chamber. I mean, you know that this section, it is the Pirani gauge chamber, and inside this chamber, we have a platinum filament. So what we have when we start the operations, so during the operation, a constant current is passed through the filament and the Pirani gauge chamber. This is the filament, and this filament, a constant current is passed. So what happens when the constant current is passed through this filament? So due to this current, the filament gets heated. I mean, this filament it gets heated and assume a resistance. I mean, when it's heated, so it assume a resistance which is measured by the Wheatstone bridge. I mean, this is the Wheatstone bridge circuit. So the resistance in this filament is being measured by the Wheatstone bridge. Then again, what happened next? Now, the pressure to be measured, that we call the applied pressure, is connected to the Pirani gauge chamber. I mean, the pressure to be measured is here is attached with this Pirani gauge chamber. And you see that this whole structure. The filament is inside, but this whole box structure is called the Pirani gauge chamber. So what is basically the function of this chamber? I mean, the function is to that is now the pressure to be measured, that we call the applied pressure, is measured to the Pirani gauge chamber. This is the Pirani gauge chamber. So due to the applied pressure, the density of the surrounding of the Pirani gauge filament changes. I mean, it's the surrounding here of the filament. So we are saying that due to the applied pressures, the density of the surrounding, I mean, these are the surrounding of the Pirani gauge filament. So its density changes. So what happened? Due to this change in the density of the surrounding of the filaments, its conductivity changes, causing the temperature of the filaments to change. I mean, let me repeat it, the process again. That is, we have the filament, and this filament we basically pass the current. So what happened? Due to the passage of the current, this filament is heated up. So we assuming a resistance. I mean, due to heating, we say that there must be some resistance, and this resistance is being measured by this Wheatstone bridge. Now we want the pressure to be measured, so it's connected to the Pirani gas chamber. The pressure to be measured is connected to the Pirani gas chamber. So what happened? Due to the applied pressures, I mean when we applied the pressure, so the density of the surrounding of the Pirani gas filament changes. So what happened? Due to this change in density of the surrounding of the filament, conductivity changes by causing the temperature of the filament to change. Then what happened next? After that, when the temperature of the filament changes, so the resistance of the filament also changes. I mean, you know that resistance is related with the temperature. So when the temperature changes, so the resistance of the filament also changes. Now, the change and the resistance of the filament is determined by using the Wheatstone bridge. I mean, these structures, the Wheatstone bridge setup is being utilized uh, to measure the change and the resistance of the filament. So then, this change and resistance of the Pirani gauge filaments become a measure of the applied pressures when calibrated. So this is how the Pirani gauge, do its operations. You can say that it's the operations of the Pirani gauges. So where we can utilize our the Pirani gauge, or what is the application of the Pirani gauge? So Pirani gauge is basically used to measure low vacuum and ultra high vacuum pressures. And we remember it's most widely utilized gauges. I mean, if you work and you live, so you will most frequently encounter this kind of gauge if you're working with any sort of the CVD system. So most of the CVD system is come with the Pirani gauges. I mean, if your vacuum is working the high gauge or even ultra high vacuum, so you will encounter with the use of this particular kind of gauge. So advantages of the Pirani gauge. So these kind of gauge, they are basically rugged and inexpensive. Uh, they give accurate results. They show a good response to pressure changes. The relation between the pressure and resistance is linear for the range of use. Reading can be taken from a distance. I mean, these are some of the excellence or merits of the Pirani gauge. But you know that just like anything else, everything in this universe they have its limitation. So just like that, we have limitations for the Pirani gauge. So these limitations include number first, it must be checked frequently, just like anything else. You utilize anything else in this universe. So for the better performance, you should check it regularly and frequently. So just like that, you can also check. You should also check the Pirani gauge. Frequently. A Pirani gauge must be calibrated for from different gases, and electric power is a must for its operations. There are some gauges where we don't need electrical power. It's basically work with the system. But here, if you want to utilize or you want to use a Pirani gauge, so be remember, uh, I mean, uh, electrical power is must for the operations of the Pirani gauge. So this all we have for the Pirani gauge and for this section. Uh, Thank you for watching. See you in next lecture. Till then, bye bye.